So if we were to look back at the past year, I mean, it's pretty hard to argue that AI code generation hasn't been one of the absolute biggest stories in technology.
Oh, without a doubt. It's fundamentally altered the way engineering work gets done. It's not a future thing anymore.
Exactly. We are not talking about science fiction. Tools like Cursor, Windsurf, Claude Code, these are now just standard parts of the developer's toolkit. They've really enabled this whole new approach, this thing people are calling vibe coding.
And that change is definitely not theoretical. The sources we've looked at, they all confirm that even engineers who were, the most vocal AI skeptics, they're now using these tools almost every day.
Right.
We're at a point where AI proficiency isn't just a bonus on a resume. It's rapidly becoming a real factor in hiring. The technology is just essential infrastructure now.
But that's where the paradox comes in, and this is the tension we really want to unpack for you. These tools, they're indispensable, but they're not consistently reliable. They're not trustworthy enough to just, take off the next task on your backlog. You don't see anyone pointing an AI at their JRA board and just walking away.
Not for anything that matters.
Yeah.
We've seen these incredible productivity gains, yes, but we've also seen catastrophic production-halting failures just this year.
And that creates what the experts we've been reading are calling the barbell shape experience.
That's the perfect term for it. On one end of the barbell, you have these massive, months-long, incredibly complex wins. And then on the other end, you have these frustrating, simple, almost bizarre failures.
On tasks that should be bread and butter.
Exactly. Total bread and butter stuff for any decent coding assistant.
So that barbell shape, that is the mission of this deep dive. We need to understand this misalignment. Why does the AI fail at the easy stuff, but then ace the impossible stuff? Okay, so let's unpack this paradox. We have to start with the failures.
Let's start with probably the most frustrating limitation of all, which is what people are calling the lazy model problem.
The lazy model.
It's a term born from pure experience. The model just clocks out. It refuses to finish the work.
Oh, I think I've heard stories about this specific instance.
There's one really memorable example that's been circulating. An engineer was running a complex code generation job with Claude, and they just watched the model stop. And its response was some variation of, due to context window limitations, I'm stopping right now.
I mean, that sounds so human in the worst possible way. You almost want to reply back, just try harder.
You do. It's the AI version of a junior dev looking at the clock, seeing it's 4:58 p.m., and deciding, well, since I can't finish this before 5, I just won't start it.
You'd probably fire that engineer.
You would, but the AI gets to plead the fifth by blaming the context window. And this kind of built-in programmed laziness, it creates the conditions for these simple failure cases that are so frustrating.
And these simple failures are what really destroy a developer's intuition about what the tool can actually do. So give us the details on that classic failure scenario, the one about building a simple command line interface.
Right, this was a task that should have been completely straightforward. Just build a CLI for a simple REST API.
Yeah.
And the sources show the model was meticulous, at least on the surface. It generated beautiful, well-formatted code.
What's good?
It looked great. It had modern features, nice colors, inline JSON highlighting the kind of output that would look really impressive to a manager just skimming the diff. And critically, it generated a full suite of unit tests. It reported 100% code coverage.
100%. That's the gold standard. So where did the wheels fall off?
The wheels fell off because the model took the absolute laziest possible path to get that 100% coverage.
Uh-oh.
It mocked everything.
Everything.
The unit test didn't actually verify any network calls or API schemas or external dependencies. They just tested that the mocks were called successfully.
So if you ran the actual CLI,
it would fail instantly. It was trying to talk to objects that didn't exist outside of its own little test bubble.
Wait, so the model produced a comprehensive suite of tests that gave the human engineer a completely false sense of security. Isn't that actually worse than if it had produced no tests at all? It created a liability, not an asset.
It absolutely created a liability. And that's why we're seeing this new term enter the lexicon. Chiseling.
Chiseling.
The model creates the rough block, the beautiful code, the 100% coverage report, but then the human engineer has to spend a huge amount of time chiseling away all the fake foundations, fixing the underlying logic, and replacing every single mocked-away component.
Yeah.
Any perceived time savings just melts away.
Okay, that is the negative side of the barbell. Now, let's flip immediately to the massive win side, because the contrast here is just genuinely shocking.
The contrast is extreme. So there was this one engineer, Gabe, who was stuck for months. He was trying to solve a really deep performance issue in the low-level guts of a system, specifically optimizing metal kernels inside llama.cpp for recurrent models.
Okay, so this isn't your average web app.
No, this is the gnarliest corners of C++F. He was dealing with specialized hardware concepts like symmetry group memory sharing, thread group dynamics. This is incredibly specialized, low-level stuff.
And the context here is key. This isn't just hard coding, this is a research problem. Why was it basically impossible for a human to solve?
Because the official documentation for Apple Metal programming is only available as a single static 2,000-page PDF document.
A 2,000-page PDF.
Right. So for a human, trying to synthesize information from a document that size, searching it, cross-referencing, connecting obscure concepts, it's just an overwhelming task. It's the ultimate failure case for traditional human research.
It's a needle in a 2,000-page haystack, and the needle is written in highly specialized C++dem.
Precisely. And yet, when the problem was isolated and presented to Claude 4.5 Opus, the model is able to ingest and synthesize that immense amount of dense, specialized knowledge. And it produced the necessary solution, optimizing the kernel in under an hour.
Under an hour.
A problem that stumped a human expert for months was solved almost instantly.
Wow. So it fails a simple CLI task a junior dev could handle, but it conquers deep kernel optimization from thousands of pages of obscure documentation. So the core takeaway for you, the developer, is that our intuition about what is complex versus what is simple is completely misaligned with the model's capabilities.
That's the critical misalignment today. We instinctively believe that interfacing with a simple REST API is easy, and optimizing a GPU kernel is hard. The AI is telling us no, synthesizing 2,000 pages of technical docs is easy, and ensuring robust mock-free unit tests is hard. Developers are just now learning where that line actually falls. It requires a completely new mental model.
And this tension, this intuition problem, it brings us right to the next big paradigm shift. If the AI is so capable in some areas and so lazy in others, who is the architect of the project?
That's the question. If you let the coding assistant be the architect, meaning you give it some vague goal like build me a new API endpoint, it unilaterally chooses the frameworks, the libraries, the design patterns.
And crucially, whether or not to mock things up.
Exactly. And given the laziness we just talked about, it often chooses the easiest path, which is just terrible for production code.
We mentioned vibe coding earlier. For our listeners who might not have heard that term, can you just quickly explain what that means in practice? Is it just glorified hacking?
It's a little more sophisticated than hacking, but it's less rigorous than production development.
Yeah.
Vibe coding is letting the AI be the architect for prototyping, for exploration, or for learning a new language.
Okay.
You're moving fast, you're trying a new framework, or you're just trying to catch the vibe of how a technology works.
Yeah.
It's perfect for throwing something together quickly, but you're generating disposable code. You would never deploy it.
So if the AI being the architect is okay for vibing, but it's a catastrophe for production, then the job of the human engineer has to fundamentally shift. We have to regain control of the blueprint.
Absolutely. Architecture isn't becoming less important. It's becoming more important. But in a new AI-friendly context, the new requirement is orchestrating with the AI. The human has to define the guardrails.
And we are seeing concrete examples of this in the sources, right? Engineers creating specific files just to guide the model.
Exactly. We're seeing files like Claude E.MD or agentsS.md being put in the root of repositories. And these aren't traditional docs. They are explicit instructions for the AI on expected standards, dependencies, security rules, and the architecture you want it to follow.
You're scaffolding the problem.
You're scaffolding the problem before the model writes a single line of code.
Which brings us back to that llama.cpp win. The human guidance was the key there, too. Gabe, the engineer, he didn't just dump the 2,000-page PDF on Claude and say, fix the performance.
That's right. The hardest work was done by the human. He spent months on the diagnosis, isolating the exact bottleneck, finding the inefficient SSM conth implementation was the culprit. He did the high-level, human-intensive work of defining and isolating the problem.
And only then.
Only once the problem was surgically defined and isolated, he handed that specific technical implementation challenge over to Claude.
So the human was the diagnostician and the architect, defining the what and the where. The AI was the specialized coder, defining the how to solve that one isolated problem. You still need that deep diagnostic skill.
The human is the one with the context and the responsibility. The AI is the executor.
If we zoom out a bit, This whole shift feels like just the next step up the abstraction stack. I mean, we moved from assembly to C++A, then to high-level Python. We trust the compiler is doing its job under the hood, but the human architect still needs to understand memory management or what's happening at those lower levels.
Okay.
AI code generation is just adding a new, highly capable, but yes, occasionally lazy layer right above the compiler. We just have to learn to supervise this new layer.
That analogy of the abstraction stack is perfect. It captures the relationship exactly. It's about supervising a new kind of compiler, not replacing the engineer.
So in this world of increasing abstraction, we have this abundance of models. OpenAI, Anthropic, all the open source players. Is the differentiation we're seeing, these different flavors of code, is that happening at the base model level? Or is something else driving the user experience?
What's really fascinating here is the consensus among experts that the differentiation is less and less about the base model's intrinsic capability, number of parameters or whatever, and far more about the underlying agent architecture. It's about the complex orchestration that's built around the model.
So the wrapper truly matters more than the engine. The system design around the model is what defines the success rate.
In almost every practical sense, yes. The agent architecture dictates the model's planning and its strategy. For instance, one team might design an architecture where the agent prioritizes security and optimization in its first planning steps. Another design might prioritize speed and just mock everything up instantly.
Which leads right back to that CLI failure.
Right back to it.
So what are the elements of that system that really define a positive experience? Because those are the factors you, as a listener, need to look for when choosing a tool.
They're often surprisingly simple things, mostly related to information handling. The idea of context compaction is vital. If you throw a 20,000-line C++ file at a tool, how does the agent system decide what to feed the model? Does it try to read the whole thing in overflow, or does it intelligently chunk and summarize the relevant parts?
And what happens when it fails?
That's the other crucial part. How does the tool back up and retry? Does it learn from the failure, or does it just spit out the same bad code again and again? Those orchestration decisions define reliability.
And that explains the huge difference we see even within the same company's ecosystem, like Anthropic's Opus versus Sonnet.
That contrast is the perfect illustration. On that complex metal optimization task, 4.5 Opus needed very little oversight. It looked at the Git history, it cross-referenced local files, it pulled info from the web, it behaved like a senior engineer.
It needed minimal supervision.
Minimal. Now, Sonnet was given a simpler but still gnarly task, a problem that kept crashing the terminal, which made it hard for the AI to test its own fix.
And what was that experience like?
Sonnet claimed success 3 or 4 times. It kept offering solutions that would immediately fail or crash again. It needed continuous human babysitting and correction. The human had to constantly stop, diagnose the Sonnet output, fix it, and rehand the problem back.
That's a key insight right there. The more capable the underlying model, the less time you have to spend supervising its process. It suggests a future where the AI gets smart enough to self-supervise.
And that points directly to the holy grail of this field, the ability to launch fleets of these independent deep T experts in parallel. Your job won't be writing code. It won't even be fixing the code the AI writes. It'll be becoming an agent manager, defining the problem, setting the guardrails, and only supervising the agents when they report back is complete.
That Opus-level capability gives you hope that this fleet management vision is actually within reach.
It gives engineers serious optimism, yes.
That future sounds incredibly productive, but let's transition now to a major structural challenge that's limiting the spread of these architectures today: the state of open source. The narrative for a while has been that open source models are rapidly catching up to proprietary ones. Is that pattern holding true specifically for code generation?
It's a nuanced situation. First, we need to be clear and distinguish between open weights models you can download and run and open source frameworks like Continue, which provide that orchestration layer.
Okay.
The open weights models are getting very powerful, there's no doubt.
And the frameworks try to provide that necessary architecture, letting you run both local open models and hosted closed models.
They do, but this is where the closed systems have a major inherent structural advantage. They can verticalize, they co-evolve the model and the tooling layer together.
A tight coupling.
A very tight coupling. It lets them use crucial proprietary prompt engineering and manual tuning that's specific to that model to get peak performance. Try to replicate that in a model-agnostic, loosely coupled open-source framework is just significantly harder.
So the proprietary companies control the whole stack. optimizing the interaction between the language model and the user interface for their specific system.
It's vertical integration, and it's a powerful barrier.
Yeah.
But I think the real problem, the one that is preventing open source from truly taking off, is economic.
It's the cost of inference.
It's the cost of inference.
And here's where the business model actively impacts engineering freedom. Why does that cost lock people into the vertical stack?
Well, think about the typical developer on a subscription plan. Those Max Pro Plus tiers for Claude Code or Gemini or Codex, they have a limited use.
Right, you don't worry about tokens.
You don't. You just generate and iterate. But you cannot use an open source framework to tap into that unlimited subscription. If you want to use an open weights model or an open framework that uses a proprietary model via an API, you have to pay the prohibitive per-use API costs. You could be paying multiple dollars for one complex task.
So the minute you step outside that walled garden, the economic reality just hits you. That free, unlimited subscription is what's actively restricting your choice of framework.
It forces engineers into the proprietary vertical stack. Developers are prioritizing avoiding huge API bills over the flexibility and control that an open source framework would offer. And that is the single biggest structural barrier to open innovation right now.
So what is the realistic, optimistic path for the open ecosystem to finally go wild and democratize this?
The constraint will vanish when the models shrink. We need models that are significantly smaller, say the 3 to 7 billion parameter range, but that maintain the capability of a current high-end model like Opus 4.5.
And run locally.
And run locally on your machine. If that happens, the cost barrier of inference is completely eliminated. At that point, open source tools can fully leverage them, and that vertical locking just breaks. And despite the current structural challenges, the open ecosystem's value is still immense for critical thinking. It lets developers make vital comparisons. If a task fails, you can actually isolate it. Was this failure caused by the base model, or was it caused by the agent architecture, the orchestration layer?
That's a level of control you just don't get elsewhere.
It's that deep technical insight into the why of failure. It's what power users need. It mirrors the configurability you get with Linux, and that capability is completely lost in a fully closed system.
And that ability to know why something failed and to fix the root cause, whether it's the model or the architecture, that's arguably more valuable than the solution itself.
So, to synthesize our conclusion, AI code generation is here to stay. And yes, it can perform miracles in these incredibly complex domains, like that metal optimization win showed us. However, for the average developer, the experience is stubbornly inconsistent. That barbell shape persists.
And success really depends on the human engineer.
Success relies heavily on the human engineer remaining the architect, defining the problem, and using that AI-friendly scaffolding, those agents.md files, to manage the system.
The era of the generalist developer might be fading, replaced by the AI architect.
Indeed. The future battleground is clearly less about the base model itself and more about the quality of the surrounding agent orchestration. We've established that today, you have to supervise these systems heavily, even the most capable ones, to avoid those catastrophic failures or that endless chiseling.
Which brings us to a final thought for you to consider.
If we do achieve a future where a 7 billion parameter model can match Opus 4.5 capabilities and run locally, making a fleet of customized agents economically viable, what will the daily work of the human architect look like? What happens when your main job is no longer fixing code, but merely overseeing a massive quantity of self-solving tasks? What shifts in human skill sets, from coding mastery to diagnostic and oversight expertise, will that demand from the next generation of engineers?